Okay, so yesterday we introduced the topic of work and also some forms of energy which we are interested in. We looked at work in terms of how much work is done. If the force and the displacement are in the same direction, we saw that in that case the work is positive and we have got maximum work done in such a direction where the force and the displacement are in the same direction. We also looked at how much work is done when the force and the displacement are perpendicular. We saw that there's zero work done in that case, and we saw that if the force is acting in a direction which is opposite to the direction of the displacement, then in such a case we end up having something called negative work. Okay. So when we have negative work, we saw that energy is not added to the system or to the object which is being displaced, but instead that particular object is going to lose energy. Okay. We looked at energy in terms of the energy you get for food. Okay, that's a chemical energy, but we're interested in two types of energies, which is the energy which an object has when it's in motion, which is kinetic energy, and the energy which an object has as a result of its position above the surface of the earth, which is what is called a gravitational field, and that's what we referred to as gravitational potential energy. So this evening we want to formalize this connection which seems to be there between the work which you do and energy. Okay, and this is formalized in the form of what is known as the WorkEnergy Theorem. Now, the WorkEnergy Theorem is also known as the principle of work and kinetic energy. Okay, so WorkEnergy Theorem is also known as the principle of work and kinetic energy. Now, what does it say? Now, the WorkEnergy Theorem says the following: if you do work on an object, and the height of that object does not change. So if you do work on an object of mass m, and the height of the object does not change, meaning that the object does not gain height or the object does not lose height. Therefore, if there is no change in height or there is no loss in height, basically there is no change in gravitational potential energy. So if you do work on an object, then this work you have done does not result in a change in gravitational potential energy. The energy that is transferred to the object is going to appear as kinetic energy. The energy transferred to the object is going to appear in the form of kinetic energy. That's what the WorkEnergy Theorem says. So if you perform work, then the object you're performing work on does not experience any change in gravitational potential energy, meaning that you're doing work on an object which is on a flat surface. Then the energy you transfer to this object of mass m as a result of the work you have done will show up in the particular object as kinetic energy. So basically it means that the object is going to move with a certain amount of velocity. So this is basically the statement of the WorkEnergy Theorem. It says the work done is equals to the change in kinetic energy. So basically that's what it is. So if your object was not moving, it was at rest, meaning that the kinetic energy of that particular object is equals to 0, then after you do work on this particular object and this object moves, it means that the kinetic energy of the object is no longer 0, but it has become something. So there's an initial value of kinetic energy when it is at rest, so 0. Now this particular object has got kinetic energy. So you can work out the change in kinetic energy as follows. The change in kinetic energy is going to be equals to the final kinetic energy of the object minus the initial kinetic energy of the object. So you always have to be aware of what is the initial kinetic energy which this particular object had before work was done, and what is the kinetic energy the object had after work is done. So here we are saying the work done is equal to the change in kinetic energy. Change in any physical quantity means that the value of this particular quantity changed. There is a final value after a certain amount of time, and there's an initial value after a certain amount of time. How do we work out the final kinetic energy, and how do we work out the initial kinetic energy? So the final kinetic energy, KEF, is equal to half mass multiplied by the final velocity squared. The initial kinetic energy, KER, is equal to half mass multiplied by the initial velocity squared. So these expressions, half mv squared and half mu squared, they give us the final and the initial kinetic energy. With these expressions, you can proceed to work out what your change in kinetic energy is going to be. The change in kinetic energy is going to be equal to half mv squared minus half mu squared, so like that. So it depends, as you can see. If the change in kinetic energy, if there is an increase in kinetic energy, then that tells you that the work which was done is positive. If there is no change in kinetic energy of an object, then it means that zero work was done. If, on the other hand, the final velocity of the object is less than the initial velocity of the object, then it means that the change in kinetic energy is going to be negative. So the change in kinetic energy can be positive if the final velocity of the object is greater than the initial velocity of the object, meaning that if there is an increase in the velocity of the object, then the change in kinetic energy will be positive. If there is no increase in the velocity of the object, the object continues to move at constant velocity without any change, then in that case there is no change in kinetic energy. And if the final velocity is less than the initial velocity, as can happen when an object is slowing down, then in that case the change in kinetic energy will be negative. So if it's positive, then it means that the work done is positive. If the work done is positive, we know what we mean. It means that energy has been transferred to this particular object. If the change in kinetic energy is zero, then it means that the work done is zero. No energy was transferred. If the change in kinetic energy is negative, it means that this particular object lost kinetic energy, meaning that the work done is negative and this particular object lost energy. Are we clear? On the statement of the work-energy theorem, yes, we have done that. Okay. Next, we have an example. Example 6. A 0.5 kg block slides across a table with an initial velocity of 0.2 meters per second and comes to rest at a distance of 0.7 meters. Find the average frictional force that retards its motion. So here we have a block with a mass of 0.5 kg, which had an initial velocity of 0.2 meters per second, and it comes to rest, meaning that the final velocity of this particular object is 0 meters per second. It comes to rest in a distance of 0.7 meters. So we want to find the frictional force. Clearly, this particular object has lost, because of the reduction in its velocity, we can see that this particular object has lost kinetic energy. So we can work out how much kinetic energy it had and how much kinetic energy it has after it has come to a stop. So the initial kinetic energy in this case, the initial kinetic energy is equal to half mu squared. In this case, our initial velocity of the block is this one, 0.2. So we end up having half mu squared equals to half 0.5, then 0.2 meters per second squared, and that gives us initial kinetic energy, which is equal to 0.01 joules. Since the block comes to rest, it means that the final velocity of the block V is equal to 0 meters per second. So in that case, the final kinetic energy, KEF, is going to be equal to half mv squared. So in this case, our V is equal to 0, so half 0.5 kg times 0 meters per second squared. This gives us a final kinetic energy of 0. The change in the kinetic energy, is going to be equal to the final kinetic energy, which is 0 joules, minus the initial kinetic energy, which is 0.01 there. So in this case, we have 0 joules minus 0.01, which gives you minus 0.01 joules as the change in kinetic energy. So you can see that the change in kinetic energy is negative, meaning that this particular object lost kinetic energy. So this is what we know in terms of energy. So we can use the WorkEnergy theorem to say the change in kinetic energy, which is what you have found, is equals to the work done. Now, what is slowing down this particular object? As we have been told, there is a friction force which is slowing down this particular object. So there is friction, and this friction, as we know about friction, is acting in the direction which is opposite the direction in which the object is moving. The distance the object slides or moves is 0.7. So this 0.7 is the displacement, and we are looking for the work done by friction. So the work done by friction is going to be equal to the friction force multiplied by the displacement multiplied by the cosine of the angle between the friction force and the displacement. Since the friction force is always opposite the direction in which the object is moving, so the angle between the friction force and the displacement is going to be equal to 180 degrees. So we can work out the work done by friction, which is equal to the friction force multiplied by the displacement, which is equal to 0.7 meters multiplied by the cosine of the angle of 180 degrees. So when you do this, this is the work done. Then we know from the WorkEnergy theorem that this work done is equal to the change in kinetic energy, which happens to be minus 0.01 joules. So we equate them here. The work done, the friction force multiplied by the displacement multiplied by the cosine of this, which is just the work done, equals to that. And cosine of 180 is negative. So we end up having the friction force multiplied by 0.7 meters times minus 1, which is what we have here. We end up with minus F 0.7 meters equals to minus 0.01 joules. There's a negative this side, and there's a negative that side. So those ones, we cancel them out. Then, of course, you divide by 0.7 on both sides. When you do that, this is what you end up with. The friction force is going to be equal to minus 0.01 joules minus 0.7 meters, and this gives you a friction force which is equal to 0.014 newtons. So you can move between the work which has been done and the change in kinetic energy depending on the direction, depending on what you have. So you can start from the change in kinetic energy part, then you move the other way where you are doing how much, you're trying to find out how much work has been done. Are we clear?
I would like you to repeat that one, sir.
Which part am I repeating?
Yes, starting from the change in the kinetic energy and the friction force, which is 0.014.
Which part have we not understood?
From the change of kinetic energy to the friction force, that side.
What have we not understood about that?
How we change from the change in kinetic energy to how we found the friction.
The WorkEnergy theorem states that here, the work done is equal to the change in kinetic energy. So if you have got change in kinetic energy on a flat surface, then that change in kinetic energy is equal to the work done. That's what the WorkEnergy theorem states. Are we clear? If you have a flat surface, then you do work on this particular object which is on the flat surface, as long as that particular object does not undergo a increase in height or a decrease in height, so that it gains or loses gravitational potential energy. When you do work, we know that work results in a transfer of energy. Okay, so if your object is on a flat surface, then you do work on this particular object. The work you have done is going to be equals to the change in in kinetic energy. So if you have done any work, that work should show itself as a change in kinetic energy. So the kinetic energy of that particular object should change. That's what the WorkEnergy theorem says, and that's what we're using. Is that clear?
It's clear now.
Yeah. So we know that the velocity when it just starts sliding is 0.2. When it comes to rest, the velocity, final velocity is 0. So the initial velocity is 0.2, the final velocity is 0. So you can work out what the initial kinetic energy is as that, 0.01. You also work out what the final kinetic energy is, which is that. So you've got the final kinetic energy, you've got the initial kinetic energy. Therefore, you can work out this quantity, change in kinetic energy. Change in kinetic energy is always the final kinetic energy minus the initial kinetic energy, which in this case is minus 0.01. So this change is negative. The reason why this change is negative is because this object lost kinetic energy. This change in kinetic energy, according to the WorkEnergy theorem, is equals to the work done. So if you have got change in kinetic energy, the change in kinetic energy is equal to the work done as a consequence of the WorkEnergy theorem. So here, the work done is equal to the change in kinetic energy, which is equal to minus 0.01. And how do we find the work in this case? What force is trying to do this negative work? It's a friction force. And when it comes to the friction force, it always acts in the direction which is opposite the direction in which an object is moving. So the work done in this case, W, is equal to the friction force multiplied by the displacement multiplied by the cosine of the angle. And the angle in this case is 180 degrees. So you end up having the friction force multiplied by 0.7 meters times cosine of 180 degrees. So this is what you end up with. The friction force 0.7 meters, then cos 180 degrees, and this is equals to the change in kinetic energy. This cosine of 180 degrees is just negative, so you've got minus F, the friction force, multiplied by the displacement equals to the change in kinetic energy. And that's how we end up having, if you divide both sides by negative 0.7 meters, you end up having your friction force as 0.014 newtons. Are we clear? Okay, next question, example, the coefficient of kinetic friction between a 900 kg car and the pavement is mu k equals to 0.8. If a car is moving at 25 meters per second along the level pavement, when it begins to skid to a stop, how far will it go before stopping? So here we've got a coefficient which seems to be unusually very high, 0.8 meters, okay? And the mass of the car is 900. The car was moving at 25 meters per second when it begins to skid to a stop. So the initial velocity of the car is 25 meters per second, and the final velocity of the car when it has stopped is of course going to be 0. So using this initial velocity of 25 meters per second and the final velocity of 0 meters per second when the car stops and the mass of the car, we can work out what the change in kinetic energy is. The change in kinetic energy is going to be equal to the final kinetic energy, which is equal to half mv squared minus half mu squared. The v in this case is the final velocity, which is 0 meters per second. The u is the initial velocity, which happens to be 25 meters per second. So you work out this change. It's going to be half 900 times 0 meters per second squared minus half 900 times 25 meters per second squared. And in this case, you end up having this, the change in kinetic energy as minus 281,250 joules. So this is how much kinetic energy this particular car loses when it comes to a stop. However, we know that this kinetic energy is lost because work has been done on this car by friction. And we have been given some coefficient of friction here, which I have said looks to be very large for a kinetic friction coefficient. So the friction force, every time you're working out at friction, friction is equal to the coefficient of friction multiplied by the normal force. And we know that the normal force is equal to basically the weight of the object. So we have a mass of 900 kgs times g, so that's going to give us the weight, then multiplied by the coefficient of friction, so that should give us what the friction force is. So in this case, your friction force is going to be equal to 0.8 multiplied by 900 times 9.8 meters per second squared. In this case, you end up having the friction force, which is equal to 7,056 newtons. So this is our friction force, and we know that this friction force is acting in a direction which is opposite. The question we're being asked is how far will the car go before it stops? So they're asking us for the stopping distance. So for us to do that, since we have got a friction force, we work out what work is going to be done by the friction. So the work done in this case is going to be equal to the friction force multiplied by the displacement, which is what you're looking for, multiplied by the cosine of the angle. And in this case, the angle between the friction and the displacement is going to be 180 degrees, since friction always opposes motion. So the work done will be 7,056 newtons multiplied by the displacement multiplied by the cosine of 180. So that is going to result in a negative. So we end up having the work done as minus 7,056 newtons multiplied by 8. So this is the work done, and we have the change in friction, which is this. So the change in friction, change in kinetic energy is minus 281,250 joules, and the work done, we have found it to be this. We apply the work energy theorem, where we know that the work done and the change in kinetic energy are equal. So in this case, you end up having minus 7,056 newtons multiplied by ACE, which is the displacement, equals to minus 281,250 joules. There's a negative, so you divide both sides, you end up having ACE is equals to minus 281,250 joules divided by minus 7,056 newtons. So this is going to give you a distance of approximately 40 meters. Is it clear on how we are applying this work energy theorem?
Clear, sir.
Okay. Next bit is something called conservation of energy. Now, with conservation of energy, what this thing says is that you cannot create energy and you can't destroy it. However, energy is always going to change from one form to another, basically. But you can change the type of energy you have from one form to another. In our case, in this course, at this stage, the interest mainly is in kinetic energy and also gravitational potential energy. Okay, so basically, if we are just focused on these two, how the kinetic energy changes and also how the gravitational potential energy changes, if you add the change in gravitational potential energy and also the change in kinetic energy, basically what you should end up with is some constant. It should always be the same. In this case, if your kinetic energy increases and your gravitational potential energy probably reduces, you end up having zero all the time. So basically, sometimes also your kinetic energy can increase and your gravitational potential energy, usually that's not how things happen. If your kinetic energy increases, it might mean that you're losing gravitational potential energy. If your gravitational potential energy increases, then most likely it means that you are slowing down and That's how you end up having something which is always constant. Either way, what you are looking at is change. You always have to remember that the change in a particular physical quantity is equals to the final minus the initial. So it's not exactly but what this thing talks about is about the change in a physical quantity. In this case, we're talking about change in kinetic energy, and you're also talking about change in gravitational potential energy. So the change in kinetic energy plus the change in gravitational potential energy should always give you the same thing. Okay, so let's see what we have here. How can we use that? Okay, here, example 8, a 1 kg projectile is shot upwards from Earth with a speed of 20 meters per second. How high is 8 when the speed is 8 meters per second? So a couple of things. We have the mass of the projectile, that's fine. But this projectile is going away from the surface of the Earth. So it has an initial velocity of 20 meters per second, and after some time, its velocity becomes 8 meters per second. So there has been a change in the velocity of this particular projectile. Its initial velocity was 20 meters per second. Its final velocity is 8 meters per second. So you can work out how the kinetic energy of this particular projectile has changed. So in this case, the change in kinetic energy is going to be equal to half mv squared, which is the final kinetic energy, minus half mu squared, which is the initial kinetic energy. So the change in kinetic energy is going to be equal to half multiplied by 1 kg multiplied by the final, which is this one here, 8 meters per second squared minus half multiplied by 1 kg times the final, which is 20 meters per second squared. So in this case, when you work out this particular physical quantity, what you get is the change in kinetic energy is equals to minus 168 joules. So this is how much the kinetic energy changes. It loses kinetic energy. So this change in kinetic energy, next here, so the change in kinetic gravitational potential energy plus the change in kinetic energy. Usually, when you add these changes, the constant we are talking about here is not some other number, but usually when you add up these changes, they usually add up to 0. When it comes to conservation of energy, they usually add up to 0. So in this case, the change in gravitational potential energy plus the change in kinetic energy is equal to 0. So the change in gravitational potential energy plus minus 186 joules equals to 0. So you end up having this. Change in gravitational potential energy minus 186 joules goes to 0. So you end up having your change in gravitational potential energy being equals to 186. This change in gravitational potential energy, you can find out how much the gravitational potential energy has changed by using this expression, the mass multiplied by g multiplied by h. In this case, our mass is 1 kg, our g is 9.8 meters per second squared, and our h is the height. This, as you can see from here, the change in gravitational potential energy, which is given by this expression, is equal to that. So, and that's what you have here. So at the end of the day, if you divide both sides by this, you end up having h equals to 186j divided by 1 kg times 9.8, and that gives you a height of 17.1 meters. So this is how you can use the principle of conservation of energy to work out the height of an object. If it's left to the ground with a particular velocity and it's somewhere in the air with a particular velocity, you can always find out at what height it is using this principle of conservation of energy. So basically, in a nutshell, the change in kinetic energy plus the change, if there is going to be change in gravitational potential energy, it means that this particular object is experiencing a change in height. Okay. With the work-energy theorem, we were restricting ourselves only to a flat surface. Say the work done is equal to the change in kinetic energy if the object is sliding or it's moving on a flat surface. In this case, the height is changing. So we are saying that the change in gravitational potential energy plus the change in kinetic energy, that should give you a 0. Are we clear? The principle of conservation of energy explains a couple of things. Most importantly, why, if your vehicle is going up a hill, it's going to slow down. Because as the vehicle is going up the hill, it is gaining gravitational potential energy. But you don't just gain gravitational potential energy from somewhere. If you gain gravitational potential energy, then you have to lose kinetic energy. So even if something just goes up, it will slow down. So if nothing is done about that, if you don't press on your gas, on your accelerator for the car, your car is going to come to a stop. So as you gain height, meaning that you're gaining gravitational potential energy, there is something which is paying for that, which is your kinetic energy. You will be losing kinetic energy. Eventually, you're going to reach maximum height. Okay. Similarly, as you come down, you are losing gravitational potential energy, but this gravitational potential energy is being transformed. It's showing up. As it's being lost, it's showing up in the form of increased kinetic energy. Are we clear?
Yes, sir.
There is also another thing, some other form of energy which is not included in here. Okay? If, for example, an object, I'll just say it, if an object is sliding on a flat surface, right? If your object is sliding on a flat surface, clearly on a flat surface, the change in gravitational potential energy is equal to 0. So on a flat surface, your object does not gain gravitational potential energy, your object does not lose gravitational potential energy. However, that does not mean that your object will continue to slide forever, because we know that if an object is sliding, it eventually has to come to a stop. So that means that that particular object actually is going to end up losing gravitational potential energy. So if the object is losing gravitational potential energy and the surface is flat, meaning that the object is not gaining if the object is losing kinetic energy because it's sliding on a flat surface and it comes to a stop, and this particular object is not gaining height or losing height, meaning that the change in gravitational potential energy is the same, where does the kinetic energy go? Because eventually this particular object comes to a stop. So far, what we have seen is that, yes, the kinetic energy is being stolen by the work which is being done by friction. That's fine. That's another way of explaining things. Say the energy is being stolen by the work done by friction. But in terms of energy, the energy which an object had as a result of its kinetic energy, where does it go? Well, if an object slides, that object is, the kinetic energy is lost as heat into the environment. So it's not that there is a way of breaking the principle of conservation of energy. No. We could have added another term here, a term for heat. Okay? So if an object slides, then it comes to a stop, it loses kinetic energy, but that kinetic energy shows up as heat, and this heat is emitted into the environment. Are we clear? At this stage, the course really does not involve much about heat, but you can always find out how much heat has been emitted into the environment by applying this conservation of energy principle. Any question?
Sir, I have a question on the surface that you talked about earlier, the flat surface. What if it is on an incline? Does it have any effect then?
Oh, if it is an incline, it has effect. Because it depends on what's happening. Is the object going up the incline? Is the object going down the incline? If the object is going up the incline, the height of the object is increasing. So the object is gaining height. If the object is gaining height, it means that the object is gaining gravitational potential energy. However, the gaining of gravitational potential energy is at the expense of kinetic energy. So if an object gains gravitational potential energy, then it means that it has to lose kinetic energy. So eventually, as this object goes up the incline, at some point it will have to stop. So you can find out, we can ask you to find out, say, oh, this particular object, when it approached the incline, it had this, at the bottom of the incline, it had this velocity. Then it goes up the incline. Then eventually it comes to a stop. Okay, so we can ask you, how high above the incline did it go? So you have to work out that thing using the principle of conservation of energy. And in that particular case also, usually you are ignoring the fact that some will tell you to ignore friction. You are ignoring the fact that most likely there's friction which is present, and friction is going to eat up some of the energy which the object had. So if it's going up the incline, the object gains gravitational potential energy, but it loses kinetic energy. If the object is coming down the incline, the object is losing height, meaning that it's losing gravitational potential energy. But as you have seen, if you're coming down an incline, you're going to experience an increase in velocity. So the increase in velocity is going to show up as a change in gravitational potential energy, which is positive. So when an object comes down an incline, it loses gravitational potential energy, but it gains kinetic energy. Does that answer the question?
Yes, sir.
Okay. Any other questions before we move on to power?
Sir.
Yes.
I wanted to find out what is the gravitational potential energy on a flat surface.
You want to find out what?
The gravitational potential energy on a flat surface.
There is no change. There is no change in gravitational potential energy. What we are interested in is a change. So if the surface is flat, you can't have any change in gravitational potential energy. So this part is equals to 0.
Okay.
Yes. Any other question?
Is there a point where the gravitational potential energy is equal to kinetic energy?
Is there a point where
The gravitational potential energy is equal to kinetic energy?
Yeah, there could be. I don't know exactly what velocity you started with, but definitely yes, you could have a point just for a short time, maybe a second, when this thing is going to be the same. That's how this thing is equal to 0. This part plus this part equals to 0. This change in kinetic energy plus change in gravitational potential energy, this constant you're talking about, this is just 0. Any other question? Okay, if there are no other questions, then we move on to power. So what do we mean by power in physics? Basically, we are talking about how fast you are doing work. And what is work? Work is you transferring energy to another object. So when you are pushing or pulling this particular object, how fast are you transferring energy? And that's what we mean by power. What we are interested in is something called average power. Average power is equals to the work done by force divided by the time taken to do that particular work. Our interest in that case, so power P is equals to W, which is the work done divided by the time. But we know how to work out the work. The work is equals to the force multiplied by the displacement multiplied by the cosine of the angle theta. We have seen different situations. If the force and the displacement are in the same direction, that's when you've got maximum work done. If the force and the displacement are 90 degrees to each other, you've got 0 work done. If it's negative, like that. So in this case, when you're trying to work out power, we are making the assumption that the force which is pushing this particular object or pulling this particular object is in the same direction as the displacement. So if the force, the applied force, is in the same direction as the displacement, then this angle theta is going to be equal to 0. So in that case, you're going to end up having F multiplied by S multiplied by the cosine of 0, and we know that the cosine of 0 is equals to 1. So you end up having power P equals to the force multiplied by the displacement divided by T. Next, we factor out the force outside, so we remain with this, the displacement divided by the time. This displacement is just the straight line distance divided by how much time it took to cover that straight line distance. So you end up seeing that displacement divided by time is what we call velocity, or average velocity. So in this case, you end up having your power equals to the force, applied force, multiplied by your average velocity. Your average velocity, you can obtain your average velocity, which is V in this case, by adding the final velocity and the initial velocity and dividing them by 2. So you get your average velocity like that. So you can get your power like this. P is equals to the applied force multiplied by the average velocity. And yeah, so there are two ways of you getting power. Either you divide, if you know what the work is, you find out the work, then you divide the work by the time, or you multiply the force times the average velocity, like that. 13 and 12, equation 13 and equation 11 give you two ways in which you can work out the power, and that's what's shown in equation 14 here. So power is equal to the weight divided by time. Basically, it's a measure of how fast you are doing work, and you can get that by multiplying your applied force times your average velocity. Any questions on that bit? The units of power are watts. And what does a watt mean? The symbol for watt is W. 1 watt simply means that you do 1 joule of work in 1 second. So basically, in this case, you are transferring, as you are doing your work, you end up transferring 1 joule of energy in 1 second. Then in that case, the power you have done is 1 watt. The issue really is when it comes to watts, watts are very, very small. But there's a more useful unit for power, which is what is called the kilowatt hour. Kilowatt hour. What does it mean? So 1 kilowatt hour in this case, basically we are talking about how much work can you do in 1 hour. If you're talking about kilowatt hour, kilowatt is power. Hour is work. So what you're doing is you're multiplying this P, you're multiplying the P here in the formula times the T here. The P is in kilowatts, then the T here is in hours. So when you multiply P times T, what you get is work. So the kilowatt hour is actually a measure of work. How much power multiplied by time. So 1 kilowatt hour is equal to this, 1000 joules per second multiplied by 1 hour. But the 1 hour itself is equal to 360 degrees, 3600 seconds. So you end up having this 1000 joules per second multiplied by 3600 seconds. When you multiply that, you end up having 3,600,000 joules. So this is how much work is going to be done. So when you buy your units in kilowatt stuff, basically that's how much you have there. So that's a very useful unit of power, the kilowatt hour. Example 9 says how large a force is required to accelerate a 1,300 kg car from rest to a speed of 20 meters per second in a distance of 80 meters. So we have a car which has got a mass of 1,300. Then it accelerates from 0 to 20 meters per second in 8 meters. Of course, in that case, we work out the change in kinetic energy. Clearly, this particular car gained kinetic energy. So we work out the final kinetic energy, which is equal to half mv squared. The final bits, then minus the initial kinetic energy, like that. So the change in kinetic energy in this case is equal to half 1,300 kgs multiplied by 20 meters per second squared minus half 1,300 kgs multiplied by 0 meters squared, and that gives you a change in kinetic energy which is equals to this much, 260,000 joules. Yeah, this is still an example of work, so I don't think this example is supposed to be. It's in the wrong. I think it's in the wrong place. Yeah. So the work done is equal to, of course, this, and in this case, whatever the force is, that's what you're looking for. Force multiplied by s, then the cosine of the angle equals to this. So we are assuming that the force and the displacement in this case are in the same direction. So F multiplied by 80 times the cosine of this, which is 0. End up that, and you end up having F times 80, which is equal to that. You divide both sides by 80, you end up having this force. But I think this example 9 is in the wrong place. It's supposed to be somewhere up there. Okay, but that's fine. Our focus is on this one, example number 10. Calculate the average power required to raise a 150 kg drum to a height of 20 meters in a time of 60 seconds. So if you have got a 150 kg drum, then you raise it through a height of 20 meters. It means that this particular drum gains gravitational potential energy. And how did it gain this gravitational potential energy? It's because you lifted it. Okay. So in this case, the lift force is equal to the weight. You are assuming that you're doing this at constant velocity, of course. So you have to work out the weight, which is equal to, weight is equal to the mass of the drum multiplied by the acceleration due to gravity. So the weight of the drum is going to be equal to 150 times that, and this gives you this much. So this is the weight of the drum pointing down. However, you can assume in this case, when you're dealing with power and stuff, you can assume that this thing was being lifted at constant velocity. So if you're lifting this thing at constant velocity, then you can assume that there is no acceleration. So if there is no acceleration, then the conclusion you make is that the lift force should be equal to the weight. So if the lift force is equal to the weight, then your lift force becomes that, 1,470 newtons. So with this force of 1,770 newtons, if you are lifting this thing up through a distance of a height of 20 meters, so your lift force is up, the displacement is up, so the angle between the lift force F and the displacement is equal to 0. So you can work out what the work is. So the work done is going to be equal to the force multiplied by the displacement, which is 20 meters, multiplied by the cosine of the angle. In this case, since the lift force is up and the displacement is 20 meters up, they're in the same direction. So the cosine of the angle, in this case, is going to be cosine of 0 degrees. You end up having your work done as 29,400 joules. So you do 29,400 joules of work. This amount of work is done in 60 seconds, which is 1 minute. So if you divide your 29,000, in this case, 29,400 divided by 60 seconds, so you end up having an average power. Power is equal to the work done divided by the time. So you're going to have 29,400 divided by 60 seconds. So you end up having a power which is equal to 490 watts. So your average power in this case is 490. We have come to the end. Are there any questions?
Yes, sir. The question.
Yes.
Like on the question, if the angle is not mentioned, we just assume that the angle is zero.
Sorry?
Mentioned in the question. If the angle is not mentioned in the question, we assume that the angle is zero there.
No, you don't assume that the angle is zero. You have to look at what's happening. So you don't just assume that the angle is zero. You have to look at what's happening. What does it take for you to lift something? Do you lift something by pushing something down or what? You pull up.
Oh, you lift.
Yes.
Yeah.
So if you're pulling up, then the object follows up, then the displacement is up and you're pulling up. So there, the force, you're pulling force and the displacement are in the same direction. If they're in the same direction, that's when you come up with the conclusion that the angle is zero. So you don't just come up with a conclusion saying that the angle is zero. No. You have to look at what's happening.
Okay, I get now, sir.
Yes. Any other question?
The question is that.
Yes. Are there any questions?
How can I calculate the power when I'm given force at the angle?
The what? Okay, I can't hear what is being said. If there's okay, we come to the end. I will try to see what I can do if you can meet tomorrow, but I'm not promising much. Okay, but we'll try. Because I've got a lot of things which have to be done. And anyway, I'm told your test is only going up to this point. Work, energy, and power. So your test 1 is only up to this point. That's what I'm told. So you might as well continue next week when you look at... but I'll see what we can do tomorrow. If we can do something. But I'm not promising much. Yeah.
Excuse me, sir.
Yes.
Yes. The coverage of the test is starting from vectors until work energy and power.
That's what I'm told.
Oh.
Yeah. Unless something changes. But that's what I heard. I was told this morning. Okay. See you tomorrow.